So this is example number 3 on circulation. In this particular example, we want to find the circulation of a velocity field around a closed rectangle shape. And I want to go around this contour. And obviously, I want to do this around counterclockwise. And if I get a negative, it's going clockwise. If it's positive, it goes counterclockwise. Actually, you could have done this either way. You could have done clockwise, but I would just let's stick with this notation. So what we want to basically do is we want to do this using the Stokes theorem. So we're going to do this using the line integral and then the double integral as well. So the first step is important to understand that we need to define the segments. The segments between 1 and 2, this point and this point, I'm going to call this segment number 1. Between 3 and 4, I will call this segment number 2. Between 2 and 1, I will call this segment number 3. Between 4 and 3, I will call this segment number 4. And it's very, very important that you see the arrows. The arrows become very important as we move forward. Okay, so we know that the total circulation will be the circulation of this velocity field along the line in 1, along the line 2, along the line 3, plus along the line 4. And if you remember, just as a review, this is nothing else than the total circulation is actually represented. This is counterclockwise. That's what this arrow around this contour will be v, velocity v dot ds. In our problem, instead of using ds, we will use r, but we are basically doing the same thing. Okay, so let's see how this actually works. We're going to go to the next page and next slide, and let's work this out. So when I begin this problem, the first thing I need to do is I need to assign the coordinates. Okay, the coordinates at this point right here will be 1, 3. The coordinates at this point will be 2, 3. That's very, very important before you actually start this problem. And what I want to do then is I want to express what the vector 1 would be. Vector 1 always would be something. If I'm going to convert this to parametric equation, it's a line. This is easy, the easiest way to do this. And this would be the initial starting point of my vector. So this is the difference of these two vectors, of the 2 points. So this will be, the first one is x, the other one is, so let me write this down here. So I am basically, this is the value in x, this is the value in y, okay? So in x, I'm going to take the subtraction, is the last point minus the first one, that would be 2 minus 1, 3 minus 3, okay? And I will start with my initial point. If this is going in this direction, so I'm really saying I am interested in the initial point. The initial point will have a value of 1 and 3, okay? So if you do the math here, and the way you do the math in this problem, just want to do one full problem, is 0, 2 times t plus 1, 3. And what you do is you multiply this t for each one of these components. Okay? So then this basically becomes 2 times t 0 plus 1, 3. Oh, I'm so sorry. This is 1. 2 minus 1 is 1. So this is t. So this whole thing, when you add vectors, you just add each one of the components. So this will be t plus 1, and this will be 3. So this is actually the value that I'm going to use for x. This is the value I will use for y. And so when I'm doing this problem, your dr1 will be nothing else than the partial of r1 respect to theta d theta. If I'm sorry, t, I'm so sorry, respect to t. And you can see that we just take the derivative of each one of these components. Okay, so it's the partial respect to t of t plus 1 over 3 dt. And what you can see is you take the derivative of the first term, okay, that will give you 1. The derivative of 3 respect to t will be 0. This is dt. So this all will be actually equal to I dt. Okay, so that's what this is all equal to. Okay, so we found this. The next thing we need to do is we need to find what the velocity vector is. The velocity vector is minus y v infinite. That's the stream velocity. When I say I have a stream velocity here, okay, v infinite, that's what the stream velocity really means. So then I have plus x v infinite. This is I, this is j. Okay, so now note that this is 3, so this becomes minus 3v I plus this is x is here, so this would be t plus 1 times v infinite over j. Okay, so what I would like to do then, I want to go ahead and I would like to just to simplify what we're going to do here is, how about we just take v, let me use a different color here, and then later we will just add them all together. So I have b dr1, I take the dot product of this and this, you can see I only have I, so I dot this will be 0, so I only have this left. So the this integral, this expression will be minus 3 dt. That's what this is equal to. Okay, we did all this just to find this term right here. Okay, so let's go to segment number 2. Okay, segment number 2, what I want to do is the coordinate system here is my beginning. If I start, the arrow goes in this direction. So this is 2, comma 3. This point right here is 2, comma 4. These are the coordinates of this point. So when I am going to create this, right? Remember, this is multiply t, and then this is my initial coordinates. The initial coordinates, because my arrow is going this direction, will be 2 and 3, because this is obviously for my segment number 2. Okay, so then this will be 2 minus 2. This will be 4 minus 1, 4 minus 3. And if you evaluate all this, you will get that this is equal to 2t plus 3. Okay, you can do the math, and that's what you will get. So now dr2 would be partial of r. Remember, we are using the chain rule. That's what we are using. dt, and there will be the partial of this from 2t plus 3 dt. That would be partial of 2 would be 0. Partial of this will be 1 dt. So this will actually equal to j dt. Okay, and then if you go to the velocity vector, the velocity vector was minus y v infinite. Let me go to the previous slide very quick. I have here, if you can fix this, I'm so sorry. There should be a v infinite times dt. You see, I have the v infinite there. I missed that. So v infinite I plus x v infinite j. So this is, so I want to replace here my x and y that will come from here. So that would be nothing else than minus, this is t plus 3 v infinite I plus x is 2, so this is 2 v infinite j. Okay, so this will be the flow regarding this segment. So what you will do now is you take the dot product of dr2, and you see this is times j, so this will only give this one term. So that will be 2 times v infinite dt. That's what you get. Okay, just take the dot product. Okay, so let's repeat the same process for segment number 3. Okay, in segment number 3, what we want to do is we want to write the coordinates again. The initial coordinates here are 2, 4, and the coordinates here are 1, 4. This is the final coordinate. So when I write my vector, I'm going to write my vector times something times t plus my initial coordinates. Again, this is only applicable for straight lines, okay? So this is my initial coordinates. That will be 2 and 4. And this coordinate then will be the final minus the initial. In the x is 1 minus 2. In the y is 4 minus 4. So when you do this, you will find that this is actually equal to minus t plus 2, 4. You can do the math, you can add this and do the math. That's what you get. This is for segment number 3. So dr of segment number 3 will be the partial of segment number 3 of dt, because I'm using the chain rule, the partial of dt of this vector plus 2, 4 dt. So you take the derivative of the first one and the second one, and that gives you minus 1, 0 dt. So that actually gives you minus I dt. Okay, so this is the value that I get for dr. And now I want to know what will be my velocity equal over that over this segment. That the problem said this is v infinite I plus x v infinite j. My y in this problem is 4, so this becomes minus 4 v infinite I. X is t minus t plus 2, so this becomes minus t plus 2 j. And now if I need to take this dot product, okay, this dot this, and you can see I only have this term that remains, and that term is actually positive term. So it becomes 4 v infinite dt. Okay, so this will be for this term right here. Okay, so let's do the last segment. Okay, so now we do segment number 4, and it's going in this direction. So my initial point will be 1, 4. Remember, this is the value in x, and this is the value in x is 1. This is coordinates is 3. So now I am going to build my vectors, again, applicable only for lines. And here I will write my initial point. My initial point is this one. This is 1 and 4. And here I will just put the subtraction of x will be 1 minus 1. This will be 3 minus 4. So then this will actually equal to 1 minus t plus 4. Okay? This is for R4. So dr4 then will be partial of R4 over dt. So it will be partial of dt, and the vector is nothing else than 1 minus t plus 4 times dt. Okay, so this will become basically the derivative of the first one is 0. Derivative of the second one is minus 1 dt, and that would be minus j dt. Okay, so the next thing I need to do is find a velocity vector that's minus y v infinite I plus x v infinite y, and this is v4 will be nothing else than, this is my y, so it's minus t plus 4 v infinite I plus x will be 1, so just v infinite j. So what I want to do now is, oh, I'm so sorry. This is actually j and j. So now what I want to do is I want to take the dot product of these two segments, okay? And the dot product between this and this will give you minus v infinite dt. Only j remains because I have a j here and a j there. So now let's go ahead and put all the integrals together and let's see what happens. So your total circulation, okay, is equal to the circulation between 0 and 1, because parametric equation we always go from 0 and 1, okay, is v1 dr1 is the vector plus 0 and 1 v2 dr2 plus 0 and 1 v3 dot d3 plus 0 and 1 v4 dot d4. Okay, so let's put here all the values back together. So the first segment would be equal to 0, 1. That was equal to minus 3 infinite, minus 3 v infinite dt plus 0 and 1. The second segment was 2 infinite, 2v infinite dt plus 0 to 1. The third segment was 4v infinite, 4v infinite dt plus his last segment will be 0 to 1, and we found that was equal to minus v infinite dt. Okay, so now I can just integrate. These are just constants, so this becomes this integration right here. This integration right here would become minus 3, and you can do that integration, plus 2v infinite plus 4v infinite minus v infinite, and you will see that this total circulation is actually equal to 2v infinite, and the units in this problem will be meters squared over second. Okay, so this is what we found using the line integral. So now what we want to do is we want to actually go ahead and use your Stokes theorem, and the Stokes theorem states the following. It says that the enclosed area, and this is why this is important, okay, of v dot ds is going to be equal to the double integral over S, the enclosed area, and this will be the integral of this uh, respect to n your ds. Okay, so this is your Stokes theorem, and so now let's use your right hand side to solve the problem. So this side, you know that in the z, because this is x and y, so this is actually equal to partial of v respect to x minus partial of u respect to y. And your problem really said your velocity field was minus y v infinite I plus x v infinite j. So if I take the partial of this respect to x, I get v infinite. Partial respect to y, I get minus v infinite. So all of this actually gives me equal to 2 times v infinite, right? Minus negative becomes positive. Okay, so this whole thing, and this is all going to be in the k, sorry, so this is a k. And this is also k because this is where your surface is applied, is going inboard, outboard. So your problem is going in this direction, so it's going inboard, outboard. So this is k as well. So if I take this and I take the dot with k, okay, you can see this gives you 2v infinite k dot k, that will give you 2 times v infinite. Okay, so that's what goes inside here. So if I go ahead to the next page and I go to integral, okay, 2 times v infinite, and this is dy and this is dx, but that's what your ds is. Your y coordinates goes from 3 and 4, goes from 3 to 4. Your x coordinates go from 1 and 2, so this goes to 1 and 2. And I can integrate the first integral inside here, and I find this gives you v, and this gives you y in terms of 3 and 4, and that gives you equal to 2 times v infinite. Okay, so then the next integral going into x will be 2 times v infinite times d of x, and that would give you 2 times v infinite times x, evaluate from 1 and 2, and that would give you 2 times v infinite. So as you can see, when I did this problem, I got 2 times v infinite. When I did the right-hand side from the Stokes theorem, I also got 2 times v infinite. Okay, so they have to give me the same answer because it's the same equation. Stokes theorem actually is equal to it's actually equal to the double integral. Okay, and that's what we call the Stokes theorem. So this concludes example number 3.